So in chemistry, we have something called the periodic table of the elements. And this is a way to systematize elements by their properties. So things that are in the same columns kind of act similar. Things that are in the same rows kind of have similar properties. And we can group elements this way. Physicists wanted a way to do this as well, but we wanted to simplify this. We want to make this easier because all of these things in the periodic table, hydrogen, helium, lithium, beryllium, they're all made of a few fundamental pieces. They're all made of these protons and neutrons and electrons. But is there something more fundamental than this? Can we break this down a little bit easier, a little bit more simply? So here we have the physicist's version of the periodic table, also called the Standard Model of Particle Physics. We have two different classifications of objects. We have things called quarks, and we have things called leptons. And these are both different kinds of particles that we use to build up the things you see in the periodic table. So we have quarks, and originally we had three of them. We had the up quark, the down quark, and the strange quark. The up and down are what we use to build protons and neutrons, and then the strange quark is a quark. It's a particle that kind of behaves a little bit strangely. It's a little bit weird. And then we found that we needed a few more particles beyond just these up, down, and strange to build all of the particles that we were observing when we were doing particle physics. So we theorized the existence of a fourth quark, something called the Charm Quark. So it was charmed because it was going to end all of particle physics and give us a complete model. Turns out that we did find the Charm Quark, and that was great, but the existence of the Charm Quark implied that there's got to be two other quarks out there. And these two quarks, originally, we had a little bit of fun, and we called them the Beauty Quark. It was going to be the fifth one, and then the sixth one was going to be the Truth, because it was going to end all of particle physics. It was going to be the last particle that we needed to find. And sure enough, it was. And in the 1990s, we found this Truth Quark, and it kind of wrapped up the model of particle physics that we currently have today. In addition to these quarks, we also have leptons. So we know inside of atoms, and we know this from our worksheets, you have protons and you have neutrons that can be built out of these quarks, right? And we have recipes for that. The up quark, two up quarks and a down quark gives you the proton, and you figured that out in these worksheets you've done. But we also need electrons inside of our atoms, right? We have electrons floating around out there. So electrons, it turns out, can't be broken down. They can't be made smaller. They're a new class of particle. They are leptons. And electrons apparently have neutrinos that go along with them. So there's electron neutrinos. But there's more particles. There's more leptons than just electrons. We have muons and we have tau particles. And each of those has a neutrino that goes along with it. So now we've got how many particles inside of our standard model? We've got 6 quarks, and we have 6 leptons. But each one of these has an antiparticle that goes along with it. They have antimatter. So each one of these 6 quarks has an antiparticle. So we have an anti-up. We have an anti-down. And so on and so forth. Same thing for charm, strange, top, and bottom. So that's 12 different quarks that exist out there. And we have the same thing with the leptons. There's antimatter versions of these leptons. So the anti-electron actually has a special name. We call it the positron. And then we have anti-muons, anti-taus, anti-neutrinos, all of these. So we have 12 leptons. So now we're up to 24 particles. Still not quite over 100 like the periodic table for chemistry, but we do have these other particles over here, these things called gauge bosons. So these are the things that make forces work, that make things actually interact with each other in the real world in physics. So we know we have protons inside of the nucleus. And the strange things about protons is they all have the same charge, so they should fly apart. The nucleus doesn't because of this gluon. The gluon is the particle that holds the nucleus together. It's responsible for the thing called the strong force. And this is the strongest force out there. Then these other particles, these other gauge bosons, we have a photon. A photon is responsible for another force called the electromagnetic force. Right? It's responsible for light. And we've learned about this already. We've learned that a photon is a particle of light. Then we have the W and Z bosons. We've learned about these already. Man, we've learned a whole crap ton of stuff this semester. These are what happens when you have radioactivity. So beta decays, alpha decays. all of those kind of decay patterns. These come from these W and Z bosons. That's what makes them work. And we call this radioactivity, give it another name. We call it the weak force. So that was the weak force that you were studying in that chapter. And then we have the fourth force. We have gravity. Gravity is not listed in the standard model, even though we know it exists out there, because we haven't found a particle to go along with it. We have this theoretical thing called a graviton, and they discuss this in the Large Hadron Collider wrap, that the graviton is super, super tiny, so it's super small, tiny little particle, and it leaps into other dimensions, which makes gravity weaker than weak. Thus, gravity is weaker than the strong force. Gravity is weaker than the weak force, rather. So we have the strong force is the strongest, second strongest is electromagnetic, third is the radioactive force or the weak force, and then we have gravity. So this is almost our complete model. We've got 12 of these quarks, plus 12 leptons, plus 3 forces, okay? And then we'll do plus 1 force that's theoretical, so we'll put that into quotation marks just because we haven't found the graviton yet. The force exists, gravity exists, we haven't found the particle. And then the last piece of the puzzle is this Higgs boson, which was discovered in 2012, the Higgs boson. This is what gives particles mass. Okay? So this is our standard model of particle physics. If you were asked to draw something like this out, what you should provide is basically this whole slide. You should create this little chart. Maybe you have 6 openings here for all of these little quarks. You have got the 4 for these forces. You've got the Higgs boson over here. You've got maybe a little space for the theoretical force due to gravity, and then you've got your 6 leptons. So what would that look like? Let's take a quick look. So if you want to draw the standard model of particle physics, you would do something like this. We have quarks, and we have 6 of them. So let's make a little box, and let's draw in our 6 quarks. And we have the up quark, the down quark, the top quark, the bottom quark, the strange quark, and the charm quark. And we should specify that we know what the names of these are. Up, down, top, and bottom. And strange, and charm. And then, these all have antiquarks. So we now have to denote that we know somehow that there are 6 antiquarks to go with it. So that's 12 total quarks. Then we also have the leptons. So let's write out the leptons and antileptons, just to specify that we know that there are antimatter particles. So there's 12 of those. And we should know what those are. So we've got, what do we have? We have the electrons, we have the muons, we have the tau, and then each of these has a neutrino that goes along with it. So we're going to specify that we know that these have neutrinos that go along. So this is almost the entire standard model of particle physics, anti-electron neutrino. We're getting close, Much, much quicker than the periodic table. Then we have the forces, right? We have these 4 forces that exist out there. We've got the strong force, and that uses a gluon. Okay, so we want 4 little boxes for this, right? So we've got the electromagnetic force, right? That's got the photon. That is the particle that makes electromagnetism work. Then we've got the W and Z bosons. And those are what make the weak force work. And these are all confirmed. And then last 2 things that we want the particle that gives things mass, right? That's the Higgs boson. And then in little dotted lines, a little dotted square. And we're going to do this. This is to get a complete model of particle physics. We want to call this gravity. We want to put this in here, but we want to say that this is theory right now. And it's only theory because we haven't found this particle that goes along with it, the graviton. Sure enough, we know gravity exists. It's a pain in the butt, especially in the winter when you slip and fall on some ice. So this is the standard model. If you were asked to write something like this on an exam, this is what you would be expected to write out.